we'd completed our mathematical foundations. So we'd completed looking at index and tensor notation. And then we had started to build our foundation to look at the motion and the deformation of a continuum, which is looking at basically the uh, kinematics of a continuum, where we discussed कि ये जो the meaning of this thing kinematics is actually when you're looking at only the sort of physical or geometric aspects of motion or deformation without any regard ke what is causing the particular deformation or motion, right? So that's why we had just started right now ke to define how can we consider the position of particles, या फिर of course a body is made up of particles, so how do we define कि वो particles हैं कहाँ? So we saw how there are these two descriptions of sort of physical properties. So either we can use our material or Lagrange description, which we saw is the one where we're referring to the original reference configuration of the reference position of the particles, and we use that to describe anything, be it कहाँ पे मैंने लिखा था, be it the temperature, be it the position, be it anything, but we will use our original reference positions to keep it sort of to describe the position of the particles. That's the Lagrange or material description. Whereas if we use the current position of a particle, then that is referred to as the spatial or Eulerian description. And I just briefly commented how the material description is used in solid mechanics more frequently, and the spatial description is used in fluid mechanics most often. Right, so this is just a little recap of what we've done. Then we looked at, there's, of course, you can consider the displacement. And then what I had started to do essentially last time was to look at, okay, it's all well and good to just look at the motion of a body, but most often what we are actually interested in, because as engineers we're going to be interested in not just the motion, but also actually probably more interested in the stresses that build up in a particular body. And we know also कि वो जो those stresses that, or the sort of um, internal loadings that might come about within a body, they arise when you have strains, right? Or what is strain? Strain is basically when something is being deformed from its reference configuration. So we saw that this is something that we're interested in, that is how the vicinity of a particle is deforming. ठीक? So we need to then start to look at the vicinity of the particle in order to describe the deformation which may be happening around it. So we started to look at that, or basically by considering the sort of how the vicinity may be changing as we go from the reference to the current configuration, we saw that there is this sort of Lagrangian or material gradient that we can define, which is the deformation gradient. Now, this deformation gradient, basically, it consists of, now let me jump right here. It consists of, where am I going to be? It consists of the sort of the change in the vicinity of a particle in the current configuration as compared to the reference configuration. Hence why this matlab, small change in the current one with respect to the reference. That is, we're basically trying to note down कि ये जो उसके the particle के इर्द-गिर्द sort of material volume थी, how is that changing when we are going to a particular different time or a current position, right? So that's what this del x by capital del x is representing, right? कि ये current configuration में vicinity को क्या हुआ है compared to, या फिर with respect to वो vicinity reference configuration में जैसी थी. Okay? So I hope this makes a little bit more sense, this deformation gradient, right? Just in case अगर किसी को भूल गया, when we just look at this del x by del small x by cap with respect to del capital X, I just want to point out that this small x, as you may recall, represents the current configuration, whereas the capital X represents the reference positions, right? So, isliye just you can note that this is looking at the change in the current with respect to the change in the original. So, just more sort of conceptual understanding or looking at what this del x by capital Del X may mean physically, right? So this is how far we'd gotten last time. We just defined this deformation gradient. Or for now, this is where I want to pick up. So just want to check again with any of you, agar if something was unclear so far, just take your questions from the previous lecture. Otherwise, we'll move on from here today. How's everybody doing? So I'm just setting up my other slides. Meanwhile, I'll wait for you to come up if you have any questions or not. All right, okay, so these were my slides from the last time. Yes, acha, no questions? Is everyone good? कोई बिलाल कोई question था last time से या अभी सब clear है अभी तक जहाँ तक हम थे?
Ma'am, I had a question, a very basic one.
जी please.
In three-dimensional tensors, going
Yes.
at the big, I mean, I can understand there are three directional dependencies, but when we go into the fourth rank, how come there are four directional dependencies, or have I got it wrong?
Yes. Okay. Let's take this one. So this is related to the fact that we had said the rank n, if we represent, of a tensor represents the directional dependencies that the tensor has, right? That's what the question is coming from. And now I think to understand this, the easiest would be to actually consider ek karke what those things are. Directional dependencies. Right. 3D से actually उसकी directional dependence का ताल्लुक नहीं है directly. Let me explain what I mean by that. So if I have a force, या फिर if I have a velocity. Now, if you notice that if I just if I use the sort of arrow graphical representation of something like that, then I know that the length of the arrow represents its magnitude, and the direction, whichever direction it may be pointing in, that is given by the direction of the arrow. Right? Now, this is a representation of a force, let's say. Now I know this is a vector quantity, right? Now I want to point out, sorry, I forgot the name of the person who was asking.
It's Usama.
Usama. So Usama, this is a force with the length is representing its magnitude and the direction of the arrow is representing its direction. Now if you notice, मैंने कोई coordinate system नहीं बनाया, मैंने कोई कुछ भी नहीं किया, और अब आप इसको देख के मुझे बताएं कि इसकी कितनी directional आपको क्या लग रहा है? एक ही direction में नहीं है वो, it's just in one direction, that's it. So this vector, या फिर अगर वो कहीं और होता, it would still just had one arrow, so to speak, which would represent कि वो resultant force या the velocity या acceleration, whatever it may be, which direction it is acting in. अगर आपने किसी को रास्ता बताना है तो आप सिर्फ एक न्यू पॉइंट करके you can just show them, right? So that's the direction. So this vector, what I'm trying to say, this just has one directional dependence. Only one. Now let's come to कि अच्छा okay, इसकी directional dependence तो one है, लेकिन if I am in 3D And if I use a if I use a coordinate system to represent this, ठीक है जी, मतलब ये कि ये तो मुझे पता है कि मैं एक एरो और लेंथ से भी रिप्रेजेंट कर सकती हूँ, लेकिन व्हाट इफ आई वांट टू बी एबल टू कंपेयर लोड्स ऑफ डिफरेंट वेक्टर्स एंड सो ऑन, और इसकी वजह या फॉर व्हाटएवर रीजन मैंने मे बी कोई ऑपरेशंस परफॉर्म करने हो, सो इट मेक्स माय लाइफ अ लिटिल इजियर टू डू इट arithmetically rather than graphically, which is why I may decide to just project this onto a coordinate system. Now if I do that, then this thing with one directional dependence will have how many components?
3.
3 components, exactly. क्योंकि वो एक डायरेक्शन को मुझे represent करने के लिए in a particular sort of coordinate system, which is not directly just aligned with f, right? It's aligned with something else. It's like with an origin, और फिर तीन right-handed तीन perpendicular directions को हम use कर रहे हैं as our basis. So then this one directional dependence tensor has a number of components which are 3. Now let's come to another sort of tensor which has a rank of 2, something which I'll tell you has a rank of 2, which is the stress tensor. Now if you notice stress tensor के साथ क्या होता है, अब ये थोड़ी सी I need your undergraduate knowledge for this. Stress tensor is something that we consider on a material particle and this is in like sort of an infinitesimal volume. And then what this means is that I'll be looking at what sort of loading is acting on each of these faces. So मतलब ये कि अगर मैं जब कहती हूँ ना कि the और ये मेरा again x y z component वैसे के वैसे ही है, let's say x y z something like this. Then when I'm plotting my stresses on this one, this face, then I'm looking at my y face, right? So उस पे I can actually consider a number of different types of loadings. One could be that your y face is being pulled like so. This one I know from my prior knowledge is something which I'm very familiar with. This is the normal stress in the y direction, sigma y, normal stress. Usko khench raha hai. Whereas I could still also be looking at this face, again the y face, but the stress in the z direction. Then I would have been looking at sigma y z. And then finally on this same face I could look at another stress, which is the same stress in the y face but in the x direction. Then that's sigma yx. My point being that if you think about it, for the stress tensor there are actually two directional dependencies. One is the face or the area on which I'm talking about, on which for which the loading I'm considering, and then is the direction on which that face is being loaded, right? So the face ki direction or phir loading ki direction, which is why stress is a second order tensor. And how many components it has?
9.
It has 9 components, yes. Why? Because there are 3 on this, 3 on this face, and 3 on this face, and so on. So this is what directional dependence means. It does not mean the number of 3D components. ठीक है जी, मतलब ये कि अगर मैं 3D, क्योंकि हम 3D में हैं, इसकी वजह से हमें मुझे अगर कोई एक डायरेक्शन को डिफाइन करना हो, I need 3 components. Whereas let's imagine some other alternate reality, very difficult to imagine, but जिसमें 4D space होती, then मेरी directional dependence जो है वो एक ही direction के लिए मुझे 4 components चाहिए होते, right? Does that make sense? So जो
Yep.
rank है ना, वो ये directional dependence represent करता है, not the number of coordinates that I need for it. Okay?
Okay, thank you. Thank you,
No
ma'am.
problem. No problem, Sama. Okay, so
अस्सलाम
that
वालेकुम
was
मैम, ये फोर्थ डिपेंडेंस टाइम होगी स्पेसिफिकली या कुछ भी हो सकती है?
ये मैंने पंडोरा's box खोला मैंने, नहीं. Fourth Okay, not quite. I'm thinking about it, but the point is that I am representing directions, right? Directional dependencies. So that's something related to space, not to time. So I'm talking about the dimensionality of space, not space and time taken together. Does that make sense?
Okay, ma'am.
Sort of. देखिए ना, मतलब एरो को मैं represent कर रही हूँ. मे बी उसकी टाइम की डिपेंडेंस हो, लेकिन मैं हर टाइम के लिए t इज इक्वल्स टू 1 के लिए आई स्टिल नीड 3 कंपोनेंट्स. फिर t इज इक्वल्स टू 2 के लिए अगर उसने चेंज कर जानी है डायरेक्शन अपनी या कुछ भी करना है जो भी, still I am in 3D space. So when I'm talking about directional dependencies, that is something to do with space, not with time. Okay. Okay. Right. So even if that's not too clear, please अपने own पे भी थोड़ा सा search कीजिएगा, right? So we are now talking about some advanced sort of courses where you do need to go into a little bit of sort of self-study mode as well. Right. Okay. So I hope that clarifies some prior questions.
मैम मेरा भी एक क्वेश्चन था.
हाँ जी, please.
मैम वैसे जब आपने स्मॉल एक्स को डिफाइन किया था तो वो रेफरेंस पोजीशन और टाइम पे डिपेंड कर रहा था,
जी जी.
लेकिन डिफॉर्मेशन ग्रेडियंट में हमने सिर्फ उसको रेफरेंस पोजीशन पे डिफाइन किया, उसमें टाइम का फैक्टर नहीं है, तो ऐसा
Yes.
क्यों है?
Yes, yes. This is a very, very good question. Very good question. Okay. Right. Let me open that slide where I've defined it. So, deformation gradient का why isn't it with respect to time, right? मतलब हम उसके time derivative में क्यों नहीं interested? So, अभी आप देखिएगा आहिस्ता आहिस्ता कि हम slowly उसमें interested होते जाएंगे. The reason why we haven't brought it up already is because we're sort of building things step by step. Or pehle we're gonna just be looking at sort of the gradients in space, yeah, changes in space, rather than the changes in time. That's one reason. So abhi we will come to that. Second reason is now this comes to the difference between solid mechanics and fluid mechanics. Now you may recall that often when we are looking at the deformation of materials, solid mechanics में, एक second मुझे एक और slide डालने देना. So when we're looking at solid mechanics and we're looking at the deformation of materials, then for the vast majority of problems, we consider that the rate of loading is at such a slow rate कि हम लोग time dependence को निकाल रहे हैं. Now, what I mean by that is, if you recall कि जब भी हम किसी चीज का stress strain curve plot कर रहे होते हैं, then for the vast majority of the problems, let's say कि steel का करें या aluminum या किसी भी चीज का, कि हम बस उसको एक चीज यूं करके प्लॉट कर देते हैं, ठीक है? और इसमें हम कोई sort of लोडिंग की बात नहीं करते कि वो किस रेट पे हुई, मतलब ये कि किस उसकी क्या टाइम डिपेंडेंस क्या थी, उस चीज की हम बात नहीं कर रहे होते. Why? Because most materials actually have a time dependent response, right? मतलब ये कि जितना ज़्यादा the rate at which you apply the loading, let's say हमें ये tensile test में से निकल रहा था results, the rate at which you're applying, the rate at which you're deforming something, that does change a little bit how the material behaves. मतलब ये if I do this at, let's say, E dot, which is approximately, it's very slow, मतलब ये कि मैं आहिस्ता 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 मटेरियल को डिफॉर्म कर रही हूँ, then I get something like this. Whereas if I deform it at some higher rate of loading, then I may get something else, somewhere like that. Now this would be for, let's say, E dot is equals to 1000 per second or something like that, right? Now this already introduces something more complicated for us, which is that the material is behaving in a time dependent manner, and that's something jo hum from the get go are not prepared to deal with. The most basic thing that we can deal with is कि material जो है वो time independent है, मतलब ये कि जो मैं उसको आहिस्ता जोर से, if I pull it at a fast rate or if I pull it at a slow rate, it gives me the same response. It's time independent. Even for 1000 पे भी वो मुझे same चीज दे रहा. So that's the initial inherent material that we look at, which is basic. ठीक है, which is time independent. तो इस वजह से initially we are just going to be interested in the changes that are occurring, that is, let's say the strains, how the length and the configuration is changing. Sorry, this was not meant to be an E right here, not an E right here, it's just, sorry, no E dot, it's just the epsilon, rather than how it changes with respect to the rate of loading of or of anything else, the rates of change. We'll slowly come to that. Okay, that's one thing. Secondly, okay, what I मुझे ये points लिखते जाने. Number one point I'm saying is okay, the most basic material, yeah, the simplest material, simplest solid material, I should put it, is time independent. सबसे simple चीज से पहले मैंने शुरू किया, इसलिए मुझे उसके rate of change, time rates में interest नहीं है अभी. Second बात ये है कि जो as mechanical engineers, the materials that we are interested in as a first priority, such as metals and ceramics at sort of room temperatures and so on, they actually have very little time dependence. I'm not saying कि completely होती ही नहीं है, लेकिन ये कि उनकी काफी low होती है. So that's also a little bit of motivation for us कि for the vast majority of problems हम time dependence of the material deformation को ignore कर दें. लेकिन just on the caveat of this कि if अगर हम biomechanical engineers होते, let's say, then I think you can all imagine कि when you have sort of soft materials and biological materials, they are highly time dependent. मतलब ये कि उनमें थोड़ी सी fluids related properties भी आनी शुरू हो जाती हैं, which is why that's why I said कि basic material time independent है. फिर as engineers अगर हम metal ceramics में interested रहेंगे, वो भी ज्यादातर cases में time independent ही हैं. Only जब हम कुछ special materials की तरफ जाना शुरू होंगे, तो फिर in solids we will need to start considering time dependencies. Okay, so that's the case for solids. पहली बात ये कि इसमें हम we have little interest in the time dependence, but we have a lot of interest in the changes in the shape and the configurations. Okay. Now let's think about what about fluids. Now what tends to happen for fluids is that actually what we are primarily interested in is exactly कि जी वो particles किस velocity से जा रहे हैं, या फिर वो particles जो हैं उनका क्या क्या होता है, और spin क्या है, या वो vortices generate हो रहे हैं उनमें, या ये हो रहे हैं या नहीं हो रहे, right? All of these things are sort of, the velocity is of course the change s dot, right? So it's the change in the position with respect to time. Let's put it in s is representing my position, right? That is, I'm interested in the rates of change. I'm interested in the time dependence. For fluids. ठीक? On the other hand, लेकिन even though I'm interested in the time dependence, the vast majority of the fluids, as we discussed in the introductory lecture, they often tend to be incompressible. या फिर the simplest fluid at least is incompressible, such that उसके अंदर जो हम deformation को देखना शुरू हुए थे अभी, ये deformation gradients को del x by del capital X, these don't really exist. And so I'm not interested in the spatial sort of या फिर deformation gradients. Instead, I'm actually interested in the time rates of changes. Okay. So wo abhi we will start to deal with the sort of the time dependence aspect of motion when we just go ahead a little bit, perhaps in a week or two, or all of that will be related to properties that we are interested in when we're looking at fluid motion basically, या फिर fluid की properties के अंदर. Whereas जब तक हम solids में हैं, then we are interested in spatial rates, but not in time rates. Does that make a little bit of sense? Yeah, that was too much of blabbering and less sensible. Please.
ठीक था मैम, समझ
समझ आ
आ
रही है?
Yes,
Thank you, sir.
Thank
Right. तो इसकी वजह से
Ma'am.
अभी जो हम जिस चीज पे बात कर रहे हैं, that is just spatial gradients and nothing to do with time gradients yet. हाँ जी, please. अभी भी some more question?
Ma'am, I was just about to ask about the impact loading. Will we be interested in the time there or not?
So that's exactly what I was saying. For particular cases, solids also have a time-dependent behavior, right? So for those kind of problems, we will be interested in the time, but we have to build these things slowly and steadily, right? जब तक हम पहले आज तक, I don't know if you guys had even heard of the deformation gradient. So only when we start to build these things up can we then move to the next step, which will be looking at the time rates, time gradients. Okay.
Okay, ma'am.
Okay. Right. So let me jump with that to the lecture for today. Hello. Yep.
Yeah, ma'am, I've got another question. Is it possible for us at all to describe the fluid motion in a material description?
Is it possible for us to describe fluid motion? So how would you come up with their initial positions? Isn't that sort of an intractable problem anyway? Just even because of Brownian motion, let's say.
So
Right?
it isn't possible then.
I would be very then maybe कोई particular example you can think of, perhaps. For example, where that आप एक initial, क्योंकि you take a snapshot and you consider that to be your time 0, और फिर उसके आगे से आप define करना शुरू कर दें हर चीज. लेकिन the issue with that is कि it's not very useful. That's the main problem for fluids. It's just not useful to start that. Yeah.
Okay, thank you.
Acha ji, now I also, okay, please, it's 5:50. I love taking your questions because they make me think as well. But we also do need to come back here. Acha, एक मुझे announcement करनी थी, which is कि I'd already uploaded the lecture. और the slides, they went up ahead of what we had done last time, right? उसके अंदर ये चीजें भी थी. I don't know if any of you have gone to see the PDF that I put up. लेकिन फिर हुआ ये कि why I did that was because I wanted you guys to read ahead, because some of you may have read up ahead, ताकि the lecture makes more sense to you. But when I started to prepare today, then I added a few things within my lecture for that day, from those slides. So what I'm going to do later, this is where we'd ended up last time. So what I'm going to do is कि मैं ना उन वाले lecture slides को remove करके ये वाली slides put up कर दूंगी. तो आप लोग please इनको download कर लीजिएगा दोबारा. So I'd put up the name as updated lecture 3 or something like that, ताकि you know कि I've added in some content in here. So for example, what I've added in is, now that we know what the deformation gradient is, I want to directly first jump and start by looking at an example. ठीक है जी. और अब इस example में भी I need to actually announce something, which is कि if you recall from our introductory lecture, there are 2 assigned textbooks for this course. One is the one by Lai, and the other one is by Reddy. ठीक है जी. So पहले मैंने पिछले वाले में ना सिर्फ Lai वाले का section लिख दिए थे कि which sections the kinematics slides, so to speak, or the things we're discussing these days are coming from. But today I also want to highlight this to you कि ready के भी अब I'm putting up के कौन से section से it's taken, because I want you to be able to read through or refer to both of these. Only then will things make more sense. Okay, this is not something जो बिल्कुल straightforward और एक ही से काफी समझ आ जाए. So that's why. Secondly, I want to just comment that the issue with continuum mechanics is, as you've already noticed with index notation and with this and that, or up deformation gradients आगे आप देखते जाइएगा, there are many sort of concepts and terminologies that we have to introduce. Generally, they are consistently used all over continuum mechanics. लेकिन कभी कभी ना फर्क लोग फर्क symbols use कर देते होते हैं. So deformation gradient के लिए जैसे you might have noticed I was using F, right? F. But I don't quite recall कि वो lie ने क्या use किया हुआ है या ready ने क्या use किया हुआ है. So please just be a little careful कि जो notation use हो रही हो वो आप उस book के उससे ज़्यादा confuse ना होइएगा. You all are master students. I'm pretty sure कि you are capable of dealing with the fact कि अगर डिफॉर्मेशन ग्रेडियंट एक में एफ का और एक में डी का हो तो आप इससे इतना कोई कंफ्यूज नहीं होंगे आई होप. ठीक है, लेकिन जस्ट बी केयरफुल दैट द notations being used in the textbooks and my slides may be slightly different. The concepts are all the same. Okay, so do take a look at ready as well. And with that, this example to encourage you to take a look at ready, I've got an example from his textbook right in here. Okay, so consider, and please all of you have pens and papers with you ताकि you can solve it before we solve it together on the slides here. ठीक है जी? Okay, so let's see. So consider the uniform deformation of a square block of side 2 units and initially centered at x is equals to 0, 0. If the deformation is defined by this mapping, okay, okay, sketch the deformation, determine the deformation gradient, and compute the displacements. Perfect. Okay. So if I find the mapping basically, usse what would I end up getting? Please notice that ये capital X के terms में defined है, right? So this is the what was it? The material description.
Lagrange.
Or Lagrangian, exactly right. So that's telling me कि अगर मुझे मेरे पास एक initially मेरे पास एक particle है उसकी कोई reference position मुझे given हो तो फिर I can use this mapping to find its, what would I be able to find its new position, right? या फिर its
Current position.
Current position, exactly right. तो अभी इसको करना शुरू करते हैं. So sketch the deformation के लिए let's first plot out actually what it is. It's the uniform deformation of a square block of side 2 units initially centered at x is equals to 0, 0. इसके अंदर if I notice सिर्फ 0, 0 क्यों given है? What about the third coordinate? I guess what's happening is कि third coordinate में कोई deformation नहीं हो रही. So what I can do is I can very neatly look at the problem in 2D. So मैं अपना coordinates को ऐसे करके define कर सकती हूँ just looking at it in a planar direction. Okay, और अब मेरे पास basis vectors are given as E1, E2 और E3 जो which will be coming out of the slides which I'm not showing. So this is my E1 and this is my E2. ऐसे ही हो गया. अब डायरेक्शंस को मुझे नाम दे दें क्योंकि यहाँ पे x1, x2, x3 करके यूज हुआ है. So I'll stick to that to make my life a little easier. So this one will be my x1 direction जिसका basis vector E1 है. And then this is my x2 direction जिसका basis vector E2 है. और अब x3 direction will come out of the slide, come out of the page from here. I'm just looking at the problem in 2D. Okay. Now, please notice this is just like my x direction and this is just like my y direction with my z direction coming out. Okay. You do recall that I said that we're just going to stick to Cartesian coordinates for ME803. Right. Okay. Let's see what it was. It was a square block of side 2 units centered at 0, 0. मतलब centered at the origin. Let's say थोड़ा सा to scale बनाते तो बेहतर होता, लेकिन मैं अंदाजों से बनाने लगी. Okay, so let's say this is my square of 2 units centered at the origin. So this is my reference configuration of my body. Okay, it's a square body and that's its reference position. Now what's happening, I know okay, it's sort of, there's a motion or there's some deformation to it such that it's given to me by this mapping. Okay, ji. So if I look at it carefully, what am I finding out? I'm finding out, for example, कि उस मैपिंग के अंदर अगर मैं कोई रेफरेंस पोजीशन इनपुट करूं तो फिर मेरी क्या करंट पोजीशन बन जाती है. और करंट पोजीशन के अंदर इफ आई लुक वेरी केयरफुली, ये बेसिस वेक्टर 1 का कोएफिशिएंट है. मतलब ये कि ये मुझे क्या देगा उसका न्यू पोजीशन का. इट विल गिव मी द
small x1.
Exactly right. It will give me the small x1 position क्योंकि ये E1 के साथ है. उसी तरह ये E2 के साथ जो कोऑर्डिनेट, जो कोएफिशिएंट है, वो मुझे उसकी x2 कोऑर्डिनेट बता देगा. और फाइनली E3 के साथ जो है वो x3 बता रहा है. ठीक है जी. सो लेट्स स्टार्ट टू प्लॉट दोज देन कि x1 तो ये हो गया, x2 ये हो गया. अब इन्हीं एक्सिस के ऊपर, ताकि मैं कंपेयर कर सकूं कि वो इधर से कहाँ जा रहा है, इन्हीं एक्सिस के ऊपर मैं अपना x1 और x2 भी प्लॉट करने लगी हूँ with the same sort of origin such that I can then see what's happening to it. Let me change my color. Right. So let's see. Let's perhaps the easiest thing to do would be कि I get my 4 corners और उन 4 corners की new position को देख लूँ. Right. So let's say कि मेरी पहली position, पहला corner जो था ये वाला, इसको मैं let's call it A. So A जो था which is -1, oh sorry, -2 comma -2, it will, oh no, square block of side 2 था. Apologies. तो अगर वो centered at the origin था तो 2 units length होने के लिए 1 unit would have gone in the plus direction and 1 unit would have gone in the minus direction. So this would have had to be -1 -1. ऐसा ही है. So if I substitute in capital X1 is equals to -1, ये देखें ना, ये capital X1 coordinate है और ये capital X2 coordinate है. और X3 क्या होगा? X3 तो वैसे ही unchanged रह रहा है. Anyway, so X1 और X2 को मैं input करूं, then I can get कि मेरा A prime, A की नई जगह, let's say current configuration में, वो कहाँ चला जाएगा? X1 को देखते हैं. X1 for A के लिए, sorry, apologies, not capital X1, small x1 उसका क्या हो जाएगा? Okay, that's what I'm trying to find. Small x1 I know is 3.5 plus capital X1 plus 0.5 x2. So substituting in -1 and -1, I get 3.5 -1 minus 0.5. क्या आ जाएगा? Please someone tell me. 2?
2 आ जाएगा.
2 आ जाएगा. Perfect. So I know कि A prime की पहला कोऑर्डिनेट क्या हो गया? 2. What about x2? उसका x2 क्या जा रहा है? x2 is just equal to x2 is just equal to 4 plus capital X2. So 4 plus capital X2, 4 minus 1, I get 3. So 2 comma 3 पे ये 1 था अगर, so 2, sorry, ओए ये तो मेरा पता नहीं इधर कहीं जाना शुरू हो जाएगा. अच्छा, 2 1 2 और फिर 1 2 3. ये this A is going somewhere like So इधर आ रहा है वो a prime है कि नहीं? Similarly, what would happen to b prime? जल्दी जल्दी अगर मुझे आप लोग बता दें, अब इनपुट ही करना है ना. b prime, b, let's call this one b, this is c, this is d. So b कहाँ चला जाएगा? b would have been 1 comma minus 1. So 3.1, 3.5, 4, 5. 5 comma x2 would have been 5.
3.
5. Oh no, 3. 3.
Yeah.
Completely right. Thank you so much. 5 comma 3. So 5, okay. 1, 2, 3, 4, 5. Or 3 would have been the same. So it would have been somewhere here. This would have been my b prime, right? Finally, c prime or d prime के लिए भी मुझे please someone, if you've already done it. C would have been 1 by 1, 5 comma 5. So somewhere here. Would have been C prime. And then D prime would have been 2 comma 5. Is this about right?
Yes, ma'am.
Perfect. So this is my new or my current configuration for this square block. Right? So ये sketch the deformation वाला part तो हमने कर लिया. Now let's any questions for the sketching part? या फिर के how did we go from the reference configuration to the current configuration? No questions. Okay, perfect. So now let's move to determining the deformation gradient. Okay, that's a little bit more involved, I guess. So I hope.
Excuse me, ma'am.
जी जी please.
मैम यहाँ हमारे एक्सिस ट्रांसफॉर्म नहीं हो रहे.
नहीं. Who is this? सामा तो नहीं है कहीं?
Nope.
दानिश.
Danish. Okay. नहीं, not quite. Please याद रखें कि हम अपने उसी sort of जब हम क्या कहते हैं, okay, let me draw it out here. If I'm looking at a body like so, उसकी current पहले reference configuration को, तो उसको भी मैं उसी space में देख रही हूँ with reference to some origin or some position, and then afterwards or from here I'm defining it to be capital X. Okay, उसकी reference position, and then even afterwards when it's deformed to somewhere else, I'm still using my same coordinate system with the same origin to represent its new position, small x. ठीक, इसी वजह से here I just taken the origin to be here. ठीक है, और फिर मैंने इसको अपनी sort of x direction और y direction से represent किया था. फिर जाहिर है मैं उसी एक्सिस के ऊपर सेम एक्सिस सेम ऑरिजिन सेम कोऑर्डिनेट सिस्टम के ऊपर उसकी रेफरेंस पोजीशन को भी बना रही हूँ और उसकी करंट कॉन्फ़िगरेशन को भी, so that I can then sort of see, okay, with my fixed frame of reference what's happening to the body. So I really don't want to be currently at least transforming my coordinates. I want to keep a fixed reference frame. Hanji. So my point is that this capital X and this capital X2 here and this capital X3, these are just representing its original position ke coordinates. Or this small x1, small x2 and small x3, they're just representing uski current configuration ke coordinates. Coordinates on the same coordinate system. Okay? Danish?
Yes, ma'am. जी मैम. Yes, ma'am. ठीक है.
Okay जी, ठीक है. Thank you. So it's clear, right? Obviously उसी वजह से तो मैं देख सकती हूँ कि वो square जो था वो actually कुछ rectangle type में deform हो गया, right? So that's of interest to me. Right, now let's jump to finding the deformation gradient. So part B is asking me find the deformation gradient f. Now I know, अभी हमने पहले पिछले lecture में किया था कि that f is actually equal to what? It's del x by del capital X, है कि नहीं? Where these are all my tensors के अंदर. So if I write it in index notation, then this is del xi with respect to del xj. That's what my deformation tensor is. Or if I expand it even more to be more pedantic, here I have, please note, I and j, two free indices. मतलब ये कि इसका rank हुआ 2, which means that it's going to have how many components? 9. मतलब मैं सारे components इधर लिखने लगी हूँ. So this is going to be del x1 with respect to del capital X1, फिर del x1 with respect to del x2, right? I or j na. So I is representing my row and j is representing my column when I'm writing it down as a matrix. So del x1 with respect to del x3, and so, sorry, this should have been a capital X, and so on for these other ones. Right? तो इसमें से मुझे जब ये सारी 9 चीजें फाइंड करनी है, then I actually need to go back to look at my how x1 is related to capital X1. That is, let's say अगर मुझे सिर्फ ये फाइंड करना हो, then I know कि my small x1 is equals to what? It's probably better if I write it down again. It's equal to 3.5, क्या हो गया इसको आज? 3.5 plus capital X1 plus 0.5 X2. So if I want to find del X1 with respect to del capital X1, then please notice, what would that be? Just 1, because this is the only term I'm interested in. And partial derivative of this term small x1 with respect to capital X1. इसी तरह आगे मुझे कहीं ना कहीं del x, आज तो ये लिखने को राजी नहीं है, x1 with respect to del x capital del x2 चाहिए होगा. And what would that be? Just 0.5. Finally, I will also need del x1 with respect to del x capital 3. What's happening today? And as you can see, there is no dependence of small x1 on capital X3. So this is equal to 0. Right? So this way, just by looking at the expression for small x1 and small x2 and for small x3, I can find their partial derivatives with respect to the reference coordinates. And then I can find कि वो f होगा क्या, right? So I'm just going to skip to the solution ताकि थोड़ा सा we can move along a little bit. So that's how I can just find each of the components for f. And if you do that, it will turn out you'll get this response, right? So for example, हमने ये del x1 की तो सारी निकाल ली थी ना, del x1, ये first row we'd already found. So del x1 with respect to capital X1 was 1, and then 0.5, and then 0. And if you see that, that's exactly what we have in the solution, 1, 0.50. Or इसी तरह we have to find the other remaining 6 components as well, right? Oh, okay. So I apologize, but clearly we had made some mistake in our. At least I had made it because nobody pointed it out to me. I told you I make mistakes when I'm working like this. So C prime or D prime में कुछ गलती हुई हुई है. Can someone tell me? C
B
prime.
prime में B prime में गलती है
B prime में B prime क्या होना चाहिए था?
4
4 होना चाहिए था. ये 5 नहीं था. Sorry. So ये 4 होके this wouldn't have been here. This would have been somewhere here. That is, we would have got something which was stretched and then sheared as well. So this is the. Sorry.
D prime में भी
D prime में भी गलती है. D prime का भी
3.
this would have been 3 5. Thank you so much. So I apologize. I was doing it a little bit quickly, so I just made some mistakes all over the place. Right. So the correct solution, of course, is the one shown right here. But I do hope कि आप लोगों को वो method or procedure समझ आ गया था, right? Which is all that we've done is we've substituted in the original coordinates of each of the corners into the mapping to find what the new positions of those corners would be. ठीक? And so we get the deformed shape, and then also from the same mapping I can identify what my x1 coordinate is, what my x2 coordinate is, small x2, and what my small x3 coordinate is, such that I can then find my deformation gradient, or that's given right here. Finally, to find the displacements, I don't think I need to explain that because we all now hopefully remember that displacement vector is just, it's the difference between the current and the reference position vector, right? Or in other index notation is small xi minus capital Xi. So just doing that, I just subtract minus x1 from this one, capital X1, so I just get 3.5 plus 0.5 x2. From here, I'd subtract minus x2, so there's just a 4, and that's it. So I get my displacement vector. Right. Any questions for this example?
Ma'am, in your first part is sketch the deformation.
जी.
उसके अंदर हम लोग सिर्फ इस वजह से 3D में नहीं गए कि हमारा जो थर्ड x3 है वो सिंपल in any case it would be x remain same.
Yes, exactly right. Because I can see from here that my small x3 is just equal to capital X3. मतलब ये है कि वो जो भी उसकी reference position 3 in the third direction, it just stays the same. तो उसमें कोई deformation हो ही नहीं रही, so then that's of almost no interest to us. That's why. You're right.
Right, ma'am. Thank you.
Also, just because हमने जब plot करना होगा तो by hand it is extremely difficult also for us to plot 3D sort of spaces and geometries, right? So we'll try to stick to 2D problems for ourselves. But of course we understand the principles now, right? So हम उसी चीज को अगर हमने कभी 3D में भी consider करना हो तो हम कर सकेंगे, hopefully. Okay, so now we've got one example out of the way, but इसके अंदर we were just sort of, it was a very substituting in values type of an example. At least हमें समझ आ गया है कि ये एक एक चीज निकलनी कैसे है. लेकिन I want to now focus a little bit on the meaning of this deformation gradient, at least in particular, because we started to define this f is equals to del x with respect to del capital X, I, and then j here. We started to define it because हम कह रहे थे कि जो खाली अगर किसी चीज का मोशन हो रहा है तो that's not of interest to us. हमें इंटरेस्ट इस चीज में है कि उसके अंदर डिफॉर्मेशंस कैसे हो रही हैं ताकि हम उसको किसी तरह स्ट्रेसेस, स्ट्रेन्स और फिर स्ट्रेसेस की तरह की अंडरस्टैंडिंग या के कॉन्सेप्ट में फीड कर सकें, राइट? सो अब लेट्स सी एक्चुअली कि ये डिफॉर्मेशन ग्रेडियंट को कुछ फिजिकल केसेस में व्हाट डज इट टर्न आउट टू बी. So I want to first start off by looking at some particular types of deformations. ठीक है जी? Now, या फिर for some particular types of motions at least. Okay. So now, first of all, I want to see that when I have a rigid body displacement. Now, please note what a rigid body displacement is. Let's change the pen color again. I think the red one works a little bit better. Right. rigid body is something जिसके अंदर कोई उसके अंदर कोई deformation ना हो, या फिर in other words there is no strain that builds up in it. As just one example, if I have a, let's say, a stick, or that stick is of like a fixed, उसके दो end points के दरमियान में कोई fixed distance है, then a rigid body displacement would be if I just take this stick and I move it somewhere here. Now there's been no change in the distance between these 2 points. And so to speak, there's been basically no deformation within this stick. All that I've done is that I've taken it from this position in space and I've put it in another position in space. So this is an example of a rigid body displacement. Clearly, it's some sort of a translation, okay? Because I'm just talking about displacements, right? Rigid body displacements, rotation ke baghair for now. So one example of, so sorry, there's a much neater sort of drawing of the rigid body displacement. One sort of mapping that could describe a rigid body displacement is the one given right here. मतलब ये कि अगर मैं x और y coordinates से represent कर रही हूँ, such that I'm going to write down my original positions with a capital X and a capital Y. So capital X and capital Y are my original positions. Then my new positions are small x and small y. ठीक? So I'm just saying कि वो जो भी capital X है उसमें 5 units translate कर दो, और जो नया y position है उसमें original वाले के अंदर 2 units translate कर दो, plus translate कर दो. So please try, if I find the f for it, the deformation tensor for it. एक तो number one कि मैं क्योंकि 2D problems कर रही हूँ, so let me just skip the third one, which would just be 0 0, and then चले मैं लिख देती हूँ पूरा, लिखने में क्या जाता है हमारा. So have a think about it, but I'm just going to jump to writing down कि वो third वाले के with respect, it would just be this 0 0 1. Let's also notice अब के इधर क्या होगा. This would be my del small x with respect to del capital X term. Like this first one would be, the first one would be del capital X. Now what is that going to be from this expression? Is this 1?
1.
Exactly. So it's just 1. ऐसा ही रह गया. And then the second term is going to be del, sorry, what would that be actually? Del small x with respect to del capital Y. What would that then be? Small x की तो dependency नहीं है कोई y के ऊपर.
0.
So it would just be, it would be 0. Or similarly, इसीलिए मैंने I already, that's why I just jumped to writing this के del x with respect to del capital Z would also be 0. And that's how I got this last column for this first row. इसी तरह for the second row, then I'm jumping to my del y's. Del y with respect to del capital X. Now again, that this small y has no dependence on capital X. So this is also 0. And then finally, what do I have here? It's del y with respect to capital Y. I say del small y with respect to del capital Y, which is going to be anyone?
1.
It's
मैम
1.
यूनिट मैट्रिक्स हमेशा रिजिड बॉडी होगी.
ये जरा पहले सवाल को आप सोच ले कि आप what are you trying to say? I'm a bit confused. यूनिट मैट्रिक्स हमेशा क्या होगी? फिर से जरा सोचिएगा जरा, जब तक मैं आ रही हूँ मैं वही, this is the point that I'm trying to make, which I think you're also trying to say, which is that we've just seen that for this rigid body displacement, if I find the deformation gradient, I just get a identity matrix. So this is just sort of, it's telling me that if I get the identity, जो अभी one of your colleagues was saying, if the deformation gradient is just an identity, then that's implying कि उस चीज के अंदर कोई deformation नहीं हो रही. ठीक, so this is a little useful because कभी भी हमारे पास f is equals to I आ रहा हो तो then we already know कि okay इसमें तो strain कोई हुआ ही नहीं, इसमें तो कोई stresses build up ही नहीं होंगे. So that's good. But let's see when we have another case of rigid body motion, but in this case it's not, oh sorry, yes, just please, yeah, read it and hopefully that'll make sense. So rigid body displacements, they do not have any impact or influence, or they don't affect the deformation gradient, which is great because that's what we want. We want the deformation gradient हमें किसी तरह eventually strains or stresses ही दे. Whereas of course rigid body displacements में कोई strain build up होता नहीं है. So this is a good sign. Check mark. Very good. But now let's see, what if we have, rather than just rigid body translations, what if we have rigid body rotation? Now when I have a rigid body rotation, then that's a motion like so. Now in this case, I'm just going to write down very quickly an example of a mapping just a rigid body displacement, rigid body rotation, sorry, mujhe milegi, and that's this, x and small y given like so. When I find the deformation gradient for this, please try it out very quickly yourself. Okay, what does the deformation gradient turn out to be for this case? I think it's going to turn out to be cos theta minus sine theta 0, sine theta cos theta 0, 0, 0, 1. That is, या फिर अगर मैं सिर्फ उसका x or y component को ही लिखूं, then I get this one, right? That is, clearly this is not equal to the identity matrix, neither is this equal to 0. And if I have different varying degrees of rotation, मतलब ये कि अगर theta change हो रहा हो, right? मतलब पहले कम rotation हो या फिर बाद में ज़्यादा हो, and so on. So मेरा deformation gradient जो है, that's changing. It's actually depending on the rotations. Now this is problematic. This is massively problematic for us because this means कि rotations से deformation gradient effect हो रहा है. Whereas we all know कि rotation जो होती है, just a rigid body rotation like this, like the one drawn here, there will be no strains built up in a rotation just like so. ठीक? So the fact that the deformation gradient actually is being affected by rigid body rotations is something which is problematic for us. So we need to think again then carefully. Acha, okay, so clearly just f as itself, just the deformation gradient as itself is not a good measure of strain. So what we need to do then is that we need to manipulate this somehow ताकि इसमें से rotations को हम eliminate कर सकें, which we will do in just a bit. Right. Let me just move to some general deformation जिसके अंदर strain भी हो रहा हो, साथ rotation भी हो, और maybe मतलब just some sort of a general deformation. और उसकी example is something like so. This is similar to the example that we just done from ready, जिसके अंदर there was shearing and some extension also happening. That is, there were some straining happening. And in that case, when I find my deformation gradient, I get some particular values. So that is the deformation gradient. It's clear to us from these examples that it's independent of rigid body displacements, but it is dependent on rigid body rotations and on strains or general sort of shear or normal sort of deformation, basically is what I'm trying to say. So मतलब ये कि हमारी deformation gradient के अंदर ही one thing, it contains the information within it which is both interesting to us, that is, it contains some information regarding this training, but which is good. But unfortunately, rotations भी उसके अंदर आ रही हैं, rigid body rotations, not just shearing, just rigid body rotations आ रही हैं, which is problematic. So we'll see how we can deal with this in just a second. Ah, yes. Okay. So one way to deal with this is कि इसी deformation gradient को हम break down कर सकें. Now you may recall from your prior, hopefully from your prior education, that matrices को हम decompose कर सकते हैं, and there are actually loads of different types of decompositions. Abhi, I will not go into sort of the proofs of that, but just for your, this is just for the sake of your understanding. कि एक particular type of decomposition is known as polar decomposition of a matrix. जिसके अंदर what we can do is we can break the matrix down into one rotation matrix and one some other symmetric matrix जो बाकी हिस्से को incorporate कर ले. Okay, so for my case मैं basically इसका मतलब ये होगा कि मैं उसी F को दो अलग इफेक्ट्स में ब्रेक डाउन करूं या डिकम्पोज कर दूं. एक के अंदर स्ट्रेनिंग इनकॉर्पोरेटेड हो या स्ट्रेन्स इनकॉर्पोरेटेड हो, और एक के अंदर रिजिड बॉडी रोटेशंस इनकॉर्पोरेटेड हो. ठीक है, सो लेट्स कॉल दोज टू डिकम्पोजिशंस, या सॉरी जो डिकम्पोजिशन के रिजल्ट होगा उन मेट्रिसेस को, एक रोटेशन मैट्रिक्स और एक में अभी सिमेट्रिक मैट्रिक्स उसका नाम देती हूँ. Now I'll call my rotation, represent my rotation matrix with the symbol R, and my symmetric matrix for now with the symbol U. Such that what I'm doing is that I'm breaking down my deformation gradient F, और अभी मैं इस particular example को use कर रही हूँ. Okay, I'm breaking it down into these two matrices. ठीक, और ये हुआ कैसे, and that's what I said कि I'm sorry but because this is not a maths course exactly, so I've skipped कि polar decomposition करनी कैसे है, लेकिन basically हमने उसकी polar क्या कहते हैं जो decompose होके product निकलता है उसको क्या कहते होते हैं, मैं भूल गई हूँ. I'm sorry, I've forgotten the name कि इन दो को क्या कहेंगे, लेकिन essentially bipolar decomposition, I found out that this F can be written as a product of these two terms, where this term is actually my rotation matrix and this symmetric term is my symmetric matrix which I'm representing as U. Now please note कि मैंने बड़े खास तौर से ना इसको लिखा है RU की terms में, मतलब ये कि F is equals to R times U. ठीक, इसी वजह से ना इस वाले U matrix को ना right symmetric matrix भी कहते हैं, because it's lying on the right hand side, मतलब बाद में multiply हो रहा है with the rotation matrix. If you look into these sort of polar decompositions in more detail, you will see that there are other types of decompositions as well. This case में I may actually be writing this down. I could, if I wanted to, I could have broken this down as F is equals to कोई और symbol अभी दे दें. I've forgotten कि convention क्या होती थी. V times R. बल्कि अब R भी नहीं रहेगा because it's not the same as this R. V times L कर लेते हैं. Let's say again it is still this L is sorry. This L is my rotation matrix, but just the difference between these two ways of decomposing it is that I've got my symmetric matrix to the right in this case where I've got U, whereas here I've got it to the left. उससे ये दूसरे वाला भी change हो जाएगा, right? So I'm just going to use this right decomposition as an example, whereas you can also do it in the left decomposition if you do want to. Okay? Right. So ये R और U हमारे पास आ गए. Oh yes. So that I was thinking it has a name. So now I've already discussed what we've managed to do by decomposing it into the rotation matrix and this U matrix is कि हमने उसके अंदर जो rotation और straining हो रही थी उन दोनों को अलग अलग कर दिया है. अब R के अंदर तो मेरी rigid body rotation चली गई है और मेरा काम आसान हो गया है क्योंकि now I've got this separate matrix, this U thingy, which is also known as the right stretch tensor. The reason being because, as I said, वो right side of the product पे appear हो रहा है, whereas ये V जो है, this is the left stretch tensor. So the right stretch tensor, it contains only the information related to deformation and straining. And that's exactly what we're interested in, because we know कि इन deformations की वजह से stress develop होता है, इन्हीं से fatigue हो रही है, इन्हीं से हमारी जो as engineers primarily जो हम चीज़ों में interested हैं वो हो रही हैं, right? Now just very quickly I want to go over के तो मतलब ये है कि ये U चीज़ जो है ना actually this U F के बजाय, because F में rigid body rotation भी थी, it's this U matrix which is the thing that we are so interested in. It's the tensor which contains information about related to straining within it. अब आते हैं इस मसले पे कि if it's so important and so useful, then why have you guys probably never heard of it before? Sorry, let me just get a sip of water. Okay. So why you've never heard of it before is because actually to find the right stretch tensor or to find this matrix U is not a straightforward problem. It's just not a straightforward problem. ठीक है जी, मतलब किसी भी particular deformation gradient को find करके उसमें से U extract करना जो है ना actually is not easy, and you need quite a lot of computational power to be able to do it. So let me just show you a process कि वैसे ये polar decomposition होनी कैसे थी. Let me first of all, if I've already got my F is equals to RU written down like so. I'm going to jump through this a little bit quickly because this is a lot of algebraic manipulation right here to do polar decomposition. Whereas as I've just told you कि हमने क्योंकि simple example ली थी इस तरह की, इसलिए अभी हम कर पाएंगे. लेकिन जब मेरे पास कोई complicated example हो तो फिर this doesn't work out so neatly, okay? So we will not be using polar decomposition in our course. I just want you guys to be able to know कि ये right stretch tensor क्या चीज़ है, how does it come, and why it's so difficult to find out. Okay. So let's just see how do we manipulate this. Let me just multiply the transpose of F with F. So this is the deformation gradient, as you all recall, right? So substituting in, then I get RU transpose multiplied by RU. Expanding this out, याद रखें कि जब transpose ले रहे होते हैं तो order of the product change swaps, right? So इसलिए ये U transpose times R transpose times R multiplied by U हो गया. Now the neat thing about this is कि जो rotation matrix है ना, R matrix जो है, the rotation matrix is always an orthogonal matrix. ठीक है जी? Please look up what an orthogonal matrix is. Basically, orthogonal matrices की ये property होती है that when you multiply an orthogonal matrix by its transpose, you get the identity matrix. So if I substitute this in here, then I'm getting basically that my F transpose multiplied by F, when I do this multiplication, उससे मैं ये R को completely eliminate ही कर देती हूँ. So I just get U transpose multiplied by U, so that I can basically manipulate it further. Now also note कि वो the right stretch tensor U was symmetric. So U transpose is also equal to U. मतलब ये कि मेरे पास this becomes FTF is actually equal to U squared. So that अब मेरे पास deformation gradient तो पहले ही find किया हुआ है ना, तो मैं उसका transpose find करके उसको multiply करके I can find के what this FTF is, and this will now be equal to the square of the right stretch tensor U squared. Now अब आते हैं इस सारा हमारी bane of the problem with the right stretch tensor is this main problem is जी
how come U is symmetric? इसकी नहीं समझ आई.
It's just the property of polar decomposition that whenever you will do that, this right stretch tensor or the left stretch tensor, either way, whenever you decompose it from the R or the in dono ke andar, this right hand side tensor or this left hand side tensor, they will always be symmetric.
Okay, thank you.
Yes, please again, I'm also not a mathematician, right? So I've just taken bits which are relevant to my physical understanding of things, but please you also go look over ke kyun polar decomposition se kyun symmetric matrix nikalti hai. I'm not sure about that. Right, so please do take a look at it. Why is U symmetric? मेरा आंसर सिर्फ ये है कि पोलर डिकम्पोजिशन में वो आता ही हमेशा सिमेट्रिक है, लेकिन I don't know why that's the case. Okay, so now when I've got my U squared, now what I can do to find my right stretch tensor is just to take the square root of this matrix, right? और इस केस में it's only for this case कि आप लोगों को नजर आ रहा है कि उसकी ये ऑफ डायगोनल टर्म्स 0 हैं, which is why इस मैट्रिक्स का जब मैं स्क्वायर निकालूं, स्क्वायर रूट सॉरी, देन आई कैन जस्ट इजीली फाइंड कि मेरी राइट स्ट्रेच टेंसर क्या है. नाउ मैंने आपको कहा था कि मैं एक बहुत ही सिंपल, मैंने जान के एक पर्टिकुलर एग्जांपल यूज की हुई है जिसमें this is the case and I can find the square root so easily. Whereas the main issue with the right stretch tensor is, sorry, once we find U तो फिर R भी हम find कर सकते हैं, sure. But the main issue with the right stretch tensor U is okay, it's actually very difficult to find the square root of a matrix for most problems unless it's some sort of a very simple case. So this square rooting of a problem jo hai, that's the square root of a matrix jo hai, that's actually a big problem for us, and that's why that's why you've never heard of the right stretch tensor beforehand. That's why we don't use it as a measure of U. Even though अगर किसी और alternate दुनिया में square root of a matrix या फिर कोई mathematician discover कर लेता है कि square root of a matrix हम किस तरह आसानी से निकाल सकें, then this U is a perfectly good measure of strain. इसके अंदर वो सब कुछ है जो हमें चाहिए to quantify sort of geometric changes, deformations happening around in the material, and उसके अंदर कोई rigid body displacements और rotations का कोई factor नहीं है, ठीक है जी. So ये वजह है कि that's why U is not used in common engineering life. But this is certainly something which हमारे predecessors actually considered. क्योंकि I hope कि now you're starting to see कि how अब आप आहिस्ता आहिस्ता, as you can see कि मैं eventually our story will lead us to the strains that we do use. But the thing is, there is all this background to how continuum mechanics developed, and we got to the strains that we do use. Okay, sometimes still there may be some problems where U still pops up, perhaps in someone's particular research or even in some old literature. So just it's good to be aware. There's also another terminology which I probably should introduce right now, which is कि जो ये मैंने ft multiplied by f किया था ना, and I saw that eliminates the rotation matrix because R transpose multiplied by R is just the identity matrix, then this FTF also is something which is important, at least in solid mechanics. And it's known as the right Cauchy green deformation tensor. Yes, really a mouthful. or you can I hope कि अभी आप shortly देखना शुरू कर देंगे कि why FTF might be important. One hint already for you guys is कि notice हमने कहा था ना कि हमें ये R के effect को eliminate करना है. So as when I was manipulating all of this on my way, I hope you noticed that when I do have the right Cauchy-Green deformation tensor, this quantity C, then even in this quantity C, there is no effect of rotation, right? So जिस तरह U was a good, useful property to have, उसी तरह even this C, the right Cauchy-Green deformation tensor, is also a perfectly good measure of strain. And indeed, in some particular problems and in some particular, I think, कुछ plasticity theories और उनको develop करने के लिए ये use भी होता है as it is. But I'll show you slowly how this term actually, this right Cauchy-Green strain tensor, right Cauchy-Green deformation tensor, sorry, is used in the strain that we're also familiar with. Okay, so let's move ahead very quickly. Oopsies, sorry, I don't have my animations in here, so meri puri slide is available for you to view right now. So I've already mentioned to you how the right stretch tensor U jo hai, this is a good measure of strain, just physically, but practically it's not very good. Why? Because it's very difficult to find it. It's very difficult to compute the square root of a matrix, and hence why हम ये use नहीं करते होते. Instead, what we do use as strain is something known as the Green or Lagrange strain tensor, Lagrangian strain tensor, very commonly just known as the Green strain tensor. Okay. Now, this I've just directly jumped to giving you the expression for this क्योंकि इसी तरह वरना हमारी story लंबी से लंबी होती जाती है कि हम कहाँ और कैसे क्यों ये पहुंच रहे हैं. Just a little bit of flavor we've already got how the history and story is progressing. So let's jump to just seeing that this is the expression for my Green strain tensor. By the way, Green was a person. So this Green strain tensor is a function of the deformation tensor, as you can see here, and also the identity matrix is also in there, popped in there. We'll see shortly why that's the case. Now, please note that this contains E is actually equal to half of FTF minus I. याद रखें कि this FTF is C. याद है वो C, अभी मैंने आपको बताया, is the right Cauchy-Green strain tensor. Again, Cauchy is a man, Green is a man, और इन्हीं दोनों के नाम पे sorry, deformation tensor. C is also named because ये यही लोग थे, Cauchy और फिर Green और all these people were involved. वो slowly पहले right stretch tensor को उन्होंने consider किया, फिर उन्होंने ये C को consider किया, उसके साथ कुछ और problems आए थे, and then finally Green strain tensor came to be used as the primary measure of strain in our lives, right? That's how the story is going, right? Now, just want to point out again that C ke andar, the right Cauchy-Green deformation tensor is FTF, which already does not have any dependence of rotation, because we saw that when we multiply the transpose of F with F, we get just U transpose times U, right? Or this U transpose times U jo hai, this contains information about the strains. This is completely independent of the rotations. So already I'm just trying to point out to you that this Green strain tensor does not have any dependence of rigid body rotation, and it only contains within it sorry it only contains within it information about deformation which causes stresses, right? Only वही strain जिसमें हम actually interested हैं. So that's why this is a good measure of how the vicinity of a particle is changing. Okay. It's nicer to just look at it in tensor notation, इसी तरह, because it's easier to read, I guess. But I also have, sorry, in direct notation, but I've also popped it right here for tensor notation because इसके अंदर it's not straightforward for me to see कि इसकी एक component के अंदर क्या होगा. Clearly, this strain tensor, it's ft transpose multiplied by f and then minus I हो रहा है. So this strain tensor is also a dyad. It has a rank of 2. So E is going to be a second order tensor. I'm telling you, we can see from here. But when I've just written it down like so in direct notation, मुझे ये नहीं पता चल रहा इससे कि E11 में क्या होगा या फिर E22 में क्या होगा या फिर E23 में क्या होगा and so on. For that, what is more useful is that I have it in my tensor notation या फिर index notation. Or index notation में if I want to find E23, then all I need to do is actually to substitute I is equals to 2 and J is equals to 3 into this expression to find कि वो मेरा exact एक component क्या होगा. Okay, so I'm just gonna go into exactly कि वो चीज़ होगी क्या, so that we can see what pops up. Yes, one last thing that I have to point out here, sorry, which is कि just by virtue of its definition, which is that it contains the transpose of something being multiplied by another thing, f. This is, whenever you have the transpose of a matrix being multiplying it by A itself, you will end up getting a symmetric matrix basically. So because of this as well, क्योंकि उसके अंदर है ही ये ट्रांसपोज की मल्टीप्लिकेशन, the green strain tensor is also it's symmetric. Okay, let me think about this again. What did I just say? I said que transpose multiplied by its with the matrix. Yes. When you multiply a matrix by its transpose, you get a symmetric matrix. Yes, I think that is true. But please just check on that. थोड़ा सा मुझे भूल रहा है हल्का सा इस वक्त. But in any case, this is always going to be true, that the green strain tensor is symmetric, flat out. और reason इसका मैं आपको ये दे रही थी कि इस product की वजह से. Right, okay. So let's just see what is contained within the green strain tensor. उसकी एक term है क्या? And with the red box right here, I hope you can notice that this is important. This is very important. I know we need to take a break. I am sorry for continuing on for so long. Just please give me 2 more minutes, then I will take take a break. No, I think I'll have to take a break now, actually. The next part also requires a little bit of... Okay, so what time is it? It's 6:50. So... Hanji, please.
Would you please go back to the last step in polar decomposition?
Sure. For everybody else, we have a break till 7 p.m. Ji.
I couldn't understand it. I mean, we are at FTF is equal to U squared, and then how did we get to the last step?
How did we get here?
Yep.
So I have a U squared की मेरे पास value है पड़ी हुई, ठीक? तो अगर मुझे U find करना है तो मुझे इसका square root ले लेना है.
That's fine. Square root हमने ले लिया. उसके बाद the last step underneath that, f into u inverse is equal to r. How come we do that?
Okay, so I know that f is equals to ru, right?
Yeah.
So if I multiply this expression by, post multiply this entire expression by u inverse, I will get fu inverse.
Thank you. Thank you. That's all. Thank you.
No problem. Right? Which is why these two. Okay, so break till 7 p.m. please. Adnan, nahi, please. Break till 7 p.m. Wouldn't you rather we finish early? Okay.
Ma'am, excuse me.
Ji, please.
Can I ask question?
Yes, yes, of course.
Ma'am, can you move back to the rigid body displacement?
Yes. Rigid body displacement. Here you go.
Yes. मैम यहाँ पे आपने लिखा है कि जब हमारे साथ f is equal to I आ जाता है तो वो हमें शो करता है कि there is like no displacement. तो ये में मतलब यहाँ से हमें मतलब कौन सी ऐसी इंफॉर्मेशन मिल रही है जो कि इस बात को इंडिकेट कर रही है कि मतलब जब आइडेंटिटी मैट्रिक्स आएगा तो लगेगा कि मतलब यहाँ पे कोई डिस्प्लेसमेंट लाइक आइडेंटिटी मैट्रिक्स में ऐसी क्या बात है कि जो
आइडेंटिटी आइडेंटिटी अगर हमारे पास f इज इक्वल्स टू आई आ रहा है ना, उससे हमें ये पता चल रहा है कि ये जो ग्रेडियंट था, मतलब ये कि एक पार्टिकल की विसिनिटी में कोई चेंज नहीं हो रहा. दैट्स व्हाट इट्स इम्प्लाइंग. व्हाई? बिकॉज उसका पार्टिकल के अगर इर्द गिर्द पहले भी हमारे पास हम इस तरह की कोई चीज को देख रहे थे, तो वो चीज न्यू कॉन्फ़िगरेशन में भी एग्जैक्टली वैसी की वैसी रह जाती है. दैट्स व्हाई रिमेंबर कि ये डेल एक्स विद रिस्पेक्ट टू कैपिटल डेल एक्स देख रहे हैं ना, मतलब dx विद रिस्पेक्ट टू dx देखा जा रहा है एक किस्म का. तो अगर ये हमारे पास 1 आ रहा है ना, सो दिस इज इम्प्लाइंग कि करंट कॉन्फ़िगरेशन में it's there is no change in this with respect to this thing. It's the same.
May I interject here?
Ji, please.
As far as I can understand here, simply the body is moving from one point to another.
Yes, so that's why I'm saying that when you have a deformation gradient which is just 1, for example here, right? So that's showing us कि उसकी अगर आप वैसी की उसका आप change with respect to x देखें तो आपको कोई change, there's nothing. It's just it's not being stretched or compressed or sheared or anything. Whereas agar if this value would have been something else, if it would have been 2, then that would have meant कि अगर हम एक hello, please keep yourself muted. That would have meant कि अगर मैं एक initially एक square को देख रही हूँ ना, तो अगर let's just consider this example, and I had gotten instead of dx is equals to dx by dx, dx would have been equal to 2, let's say, rather than 1 जो identity में आता है, then that would have meant कि वो initial square जो है वो actually उसकी x direction में increase हो गया है, extend हो गया है. एक नॉन 1 वैल्यू से ये शो हुआ होता. ठीक. सो दैट्स व्हाई ये आइडेंटिटी आने से हमें इंडिकेट कर रहा है कि ओके x विद रिस्पेक्ट टू x वैसे ही रह रहा है मतलब इट जस्ट स्टेज एज अ स्क्वायर, व्हेयरएज x विद रिस्पेक्ट टू y उसमें कोई चेंज ही नहीं आ रहा है, इट्स जस्ट 0. I feel like I'm unnecessarily complicating it by explaining it कि इसमें कोई physical meaning क्या आएगा in each of these things. Just basically take it to understand कि when we get the identity matrix, then it just flat out it just tells us कि there's only rigid body displacement happening. Nothing, no extension, shear or
Ma'am? I have a question here.
एक second, just pause for a second, Adnan.
Okay,
Let's just digest what we just were saying, right? So when we're just getting I, so just 1, 1, 1 on the diagonals and zeros elsewhere, then that just shows us it's only one thing has been picked up from one place and put somewhere else. There's no scaling, there's no sharing, there's no extension, none of that. वो body की geometry वही रहती है as its reference configuration. जी please Adnan.
मैम माय क्वेश्चन हियर इज कि हम फिजिकली देख सकते हैं कि यहाँ पर क्या हो रहा है, लाइक बॉडी इज हैविंग सम ट्रांसलेशनल मोशन एंड डिफॉर्मिंग एज वेल, बट कैन ये तो फिजिकली हो गया, लेकिन इसकी प्रैक्टिकली कोई एग्जांपल किस तरह की होगी, लाइक प्रैक्टिकल हमें आगे कहाँ पर ये अप्लाई होंगी, तो मैं ये पूछना चाह रहा हूँ।
अदनान ये प्रैक्टिकली इस तरह अप्लाई होगी कि हम सारी जिंदगी से स्ट्रेसेस निकालने की कोशिश में लगे हुए हैं एज मैकेनिकल इंजीनियर्स, और हमें ये पता है कि स्ट्रेसेस वहीं जनरेट होंगे जहाँ पे स्ट्रेन्स होंगे या फिर जहाँ पे आपकी मटेरियल बॉडी एक खास तरीके से डिफॉर्म करती है. दैट इज इट्स नॉट जस्ट रिजिड बॉडी डिस्प्लेसमेंट से कोई स्ट्रेसेस नहीं जनरेट होते. इट्स ओनली व्हेन देयर इज सम सॉर्ट ऑफ some sort of scaling or shearing that's happening that leads us to stresses, right? So that's why we're obsessed with this. हमें कोई ऐसा measure of deformation चाहिए जिससे हम stresses निकाल सकें, इसलिए हम इसमें interested हैं. ये सवाल होगा कि हम stresses और strain में क्यों interested हैं.
नो मैम, मेरा क्वेश्चन यहाँ पर ये है कि जिस तरह आपने हम पहले देख रहे थे कि एक बॉडी है वो लीनियर भी मोशन हो रही है एंड एज वेल एज उसमें डिफॉर्मेशन भी हो रही है, ठीक है, तो वो दोनों एक दूसरे के ऊपर डिपेंडेंट भी है समहाउ, क्योंकि वो मैपिंग के ऊपर डिपेंडेंट है, ऐसे ही है ना मैम? ठीक है, लीनियर मोशन इटसेल्फ एंड द डिफॉर्मेशन एज वेल दोनों ही डिपेंडेंट है मैपिंग पे, ऐसे ही है मैम? तो इस तरह की मैं किसी एग्जांपल का पूछना चाह रहा था कि जिसमें हमारे पास लीनियर मोशन भी हो रही है एंड डिफॉर्मेशन भी हो रही है, दोनों, और दोनों मतलब डिपेंडेंट भी हैं दूसरे पर, तो इस तरह की कोई एग्जांपल मैं चाह रहा था बेसिकली।
अदनान, उसके लिए आप सिर्फ इसी के अंदर एक प्लस ट्रांसलेशन ऐड कर दें, खाली इसमें +2 लिख दूं, +3 लिख दूं, उससे वो यही चीज उठ के इधर भी चली जाएगी साथ ही. ये लें, आपकी लिनियर भी हो गई और साथ डिफॉर्मेशन भी हो गई.
मैम मैं ये कह रहा हूँ कि ठीक है आपने लिख तो दिया, लेकिन लीनियर मोशन को इसमें इंटीग्रेट करके हमें क्या मिला, ये तो सिर्फ हम थोड़ा सा कॉम्प्लिकेट कर रहे हैं, नथिंग एल्स.
अदनान, मुझे आपका सवाल नहीं समझ आ रहा, आप क्या पूछना चाह रहे हैं.
चलिए मैम, मैं कल थोड़ा सा इसके बारे में सोच के अगेन आपसे क्वेश्चन करूँ.
श्योर. आपको ये बात तो क्लियर है ना कि हमें जो खाली ट्रांसलेशन वाला पार्ट है उसमें इतना इंटरेस्ट, मैं आपको कह रही हूँ कि उसमें सिर्फ इंटरेस्ट है टू द एक्सटेंट कि हमें उसकी पोजीशन चेंज चाहिए हो अगर, तो दैट्स इट, जो हमें उसके इन एक्स और वाई से ही पता चल जाएगा. लेकिन एज सून एज मुझे उसके अंदर जो स्ट्रेसेस डेवलप हो रहे हैं वो चाहिए, उसके लिए मुझे कोई दैट्स व्हाट आई एम ट्राइंग टू गेट टू, राइट? कि आई वांट टू फाइंड दिस मेजर ऑफ डिफॉर्मेशन जिससे मैं इवेंचुअली उसके अंदर जो स्ट्रेसेस या लोडिंग बिल्डअप हो रही हो वो फाइंड कर सकूं, राइट? विच आई नो के अगर मेरे पास खाली उसका पाथ गिवन हो या फिर ये एक्स और वाई नोन हो कि उसने नई उसकी ये पोजीशन हो जाती है, तो इससे तो मुझे नहीं कुछ पता चल रहा ना, इससे तो मुझे नहीं पता चल रहा कि उसके अंदर, मतलब इससे आई कांट रियली टेल डायरेक्टली कि वेदर व्हाट द स्ट्रेसेस वुड बी डेवलपिंग इन इट. So I do need some way to remove rigid body displacements and rotations from the straining, which is what we're trying to get to.
ओके मैम, यू आर सेइंग दैट ये डिफॉर्मेशन ग्रेडियंट जब हम निकालते हैं तो ये ट्रांसलेटरी पार्ट अपने आप ही निकल जाता है,
नहीं,
लीनियर मोशन
तो मसला था कि डिफॉर्मेशन ग्रेडियंट के अंदर अभी हमने देखा कि उसके अंदर रोटेशन उसको अफेक्ट कर रही है अभी भी ये देखें ना,
लेकिन लीनियर मोशन का पार्ट तो निकल जाता है, आप ये बता रहे थे.
लीनियर पार्ट निकल गया, श्योर. हाँ बिल्कुल ठीक.
ओके ओके
लेकिन अभी भी that's still not enough for us, you know, do you see, because rotations are still affecting.
वो तो ठीक है मैम, मैंने तो सही है ना, मुझे इस बात से बिल्कुल एग्री कर रहा हूँ कि लीनियर पार्ट निकल गया, लेकिन सर मेरा मैम यहाँ पर क्वेश्चन ये था कि लीनियर और दोनों की इकट्ठे ही चल रहे हैं एक ही कोर्स मैपिंग के ऊपर, एक ही सॉरी वो जो मैपिंग है उसके ऊपर डिपेंडेंट है, इसकी कोई एग्जांपल अगर मिल जाती दैट वुड हैव बीन गुड एनफ। ठीक है, सिर्फ मैंने इतना ही पूछा। हमने जहाँ से स्टार्ट किया बेसिकली, जो हमारा स्टार्टिंग पॉइंट था उसकी एग्जांपल पूछ रहा था। स्टार्टिंग
मुझे
पॉइंट से
ना आपका ये सवाल इसलिए नहीं समझ आ रहा क्योंकि आपको ये नजर आ रहा है ना कि मैपिंग्स तो ये रही ना कि उसकी करंट पोजीशन क्या बनती जा रही है, तो ये तो इट्स जस्ट गिवन बाय सम सॉर्ट ऑफ जो भी पर्टिकुलर मोशन हो रहा है उसकी एक्सप्रेशन से गिवन है। तो इसीलिए तो मैं आपको कह रही थी कि अगर आप चाहते हैं कि जी लिनियर भी हो इन एडिशन टू एक्सटेंशन एंड सो ऑन, तो बस आप उसमें इस तरह अगर मैं कोई स्केलर टर्म सिर्फ ऐड कर दूं ना, तो उससे आई विल गेट बोथ लिनियर, just translation you mean, by the way, you mean rigid body displacement, it's not linear, that there's no such thing. You will get a rigid body displacement and I'm still getting I've got rotation and I've got scaling in here. तो इसके अंदर in this particular जो with the +2 and the +3 I have rigid body displacement, I have rigid body rotation and I have straining in this mapping. ये mapping है, ये mapping लिखी हुई है।
ओके मैम।
Right. Okay, so I hope everybody is back. So it's 7:03, so you must be back, inshallah. So let's pick up where I'd left off. Okay. Yes, so we've gotten to our green strain tensor. Which the beautiful thing about that is it does not have any rigid body rotation or rigid body displacement effect within it. So given a particular mapping, we जो अभी अदनान कह रहे थे कि अगर हमारे पास कोई mapping known हो, उससे हम deformation gradient निकाल सकते हैं, and once we've got our deformation gradient, then I can find what are the strains being developed in that particular body just by using this green strain tensor. अब let's see how we can, मैं आपको कही थी कि मुझे देखना है कि उसकी एक एक टर्म के अंदर है क्या, to sort of understand it a little bit more. But in order to do that, I'm still gonna carry on इधर उधर थोड़ी सी manipulation के साथ कि perhaps first let me change it ताकि वो मेरी deformation gradient के बजाय मेरी displacement की terms में भी given हो, just out of interest, just for a second, please allow me. Now you may all maybe you don't recall this, but जहाँ पे हमने अपना deformation gradient को derive किया था ना in slide 9, I think it was in the past somewhere. Let me just show you. कितनी सारी हो गई in slide 9. So right here when we were deriving this, we'd also considered कि हमें इसी deformation gradient को हम displacement की terms में भी लिख सकते हैं in terms of u. So let me do that. Let me start to let me start to manipulate my green strain tensor using my expression for the deformation gradient in terms of their displacement. ठीक है जी। अब I know कि बहुत सारी index notation यहाँ पे pop कर रही है, but मैं अभी I don't expect this level of competency in index notation कि हम लोग ये क्यों f को k I k j लिखा हुआ है, सोचिएगा इस पे जरूर, या फिर जस्ट देखिएगा कि ट्रांसपोज मल्टीप्लाई बाय मैट्रिक्स कर रहे हो तो उसको इंडेक्स नोटेशन में लिखते कैसे हैं, ठीक है। बट बेसिकली ट्रस्ट मी फॉर दिस फॉर नाउ कि ये दिस इज व्हाट इट टर्न्स आउट टू बी। ओके, सो लेट मी मैनिपुलेट दिस इन इंडेक्स नोटेशन क्योंकि उसका मुझे थोड़ा सा फायदा होगा अभी आहिस्ता आहिस्ता। तो अभी मैं क्या करने लगी हूँ, मेरे जहाँ पे एफ के आई एफ के जे हैं उसके अंदर मैं ये एक्सप्रेशन सब्स्टिट्यूट करने लगी हूँ। ओके, सो देयर इज गोइंग टू बी क्वाइट अ बिट ऑफ जस्ट algebraic manipulation basically. तो अब now I have a product written in index notation, तो उसको मुझे expand करने दें, then I just get delta ki multiplied by delta kj here, फिर डेल्टा के आई मल्टीप्लाइड बाय यू के कॉमा जे, यू के कॉमा जे ये आ गया, फिर ये वाला प्रोडक्ट, फिर ये आखिरी प्रोडक्ट, ये 4 प्रोडक्ट्स आ गए, माइनस वो डेल्टा आई जे उधर का उधर ही रहा. नाउ एज यू मे रिकॉल के हमारे पास कुछ आइडेंटिटीज हैं फॉर द Ronecker delta. Please also, wherever there's going to be this delta, that is going to mean Ronecker. Whenever I've got it with some sort of ij and so on, okay? So using those identities, I can manipulate this further because I know कि ये जो चीज़ है ना, this also actually becomes just delta ij. So I've got a delta ij here, I've got a delta ij there, subtracting from each other, so they cancel out. The remaining 3 terms may, whenever you have the Ronecker delta being multiplied by something, फिर उसकी क्या आइडेंटिटी थी, ओहो मुझे भी वो लिखी हुई चाहिए वरना आई ऑल्सो फॉरगेट देम समटाइम. सो आई थिंक कि एक आइडेंटिटी थी कि डेल्टा आई जे being multiplied by, हाँ मुझे ऑलरेडी भूलना शुरू हो गया, आई के let's say, then this would give me u j k. That is वो I वाला just disappears and this stays the way it is. So this term then becomes U, मैंने कहा ना K just disappears, K की जगह जो भी जिस पे डमी था उसकी जगह जो Ronecker के अंदर दूसरा रह गया था वो आ जाता है. So I get U I comma J plus here इसमें K common है तो J इधर आ जाएगा U J comma I plus more manipulation. This one stays the same, सिर्फ ये U के अंदर. So U K comma I multiplied by U K comma J. I know this looks कि पता नहीं कोई जादू कर रही है इधर से उधर ही क्या छलांगे मार रहे हैं, but just for anybody who is interested in the arithmetic manipulation, I've left it here. लेकिन I'm not too overly concerned कि आप लोग ये part के ऊपर बहुत ही obsess करें ज़्यादा, ठीक है? Just trust me when I just check this, but just trust me कि this is how the arithmetic manipulation will work out. Okay, so do try it. अगर बिल्कुल ही कुछ समझ नहीं आता और बिल्कुल ही crazy लग रहा है, फिर do talk to me. Okay, you will need to go back and refer to the index notation lecture to understand it completely because वो हमें identities चाहिए Ronecker delta की. Okay. So basically we get this result. और I hope कि अब आप लोगों को समझ आ रहा है कि क्यों हमें वो पहले से इंट्रोड्यूस करना थोड़ा सा जरूरी था, क्योंकि हमने बहुत सारी मैनिपुलेशंस करनी होती हैं इन कंटिन्यूम टू गेट फ्रॉम वन रिजल्ट टू द अदर. So I get this expression right here. Perfect. Now just because I know कि थोड़ा फिजिकल अंडरस्टैंडिंग को इम्प्रूव करने के लिए इट मे बी हेल्पफुल कि मैं ये कॉमेज को हटा के जरा लिखना शुरू कर दूं कि what are these differentials exactly. So if I do that, then let me just sort of write it out in expanded calculus notation. Then I get that this ui comma j is of course the differential of ui with respect to del xj. और नोट कि ये कैपिटल x के विद रिस्पेक्ट डिफरेंशिएशन है बिकॉज हम ये f पे थे ना, राइट? आई रिमेम्बर कि ये मैंने पहले इधर आप लोगों को बताया था कि f इज डिफरेंशिएशन विद रिस्पेक्ट टू कैपिटल x ना. So that's why this ui was also this, all of this was basically differentiation with respect to capital X. Hence why I've got it like this. So पहली term तो ये हो गई. दूसरी term is del uj with respect to xi, and then finally ये वाली क्या होगी uk with respect to xi and uk rho, something pretty complicated when I write it out in terms of the displacement vector. But there's a reason why I'm doing this because I hope you will see shortly के क्या, what does this mean. Let's keep an eye out के if I start to now expand each of the terms, that is if I want to start to find कि E11 क्या है, E12 क्या है, and so on, then I just can substitute in my I and my J in here. So let's do that. So ये आई जस्ट सॉरी, मैंने पिछली वाली ही एक्सप्रेशन से इधर लिख लिया है, ठीक है जी। ये ई आई जे जस्ट फ्रॉम माय लास्ट स्लाइड है राइट हियर, या फिर आई ऑल्सो डू वांट टू राइट इट इन मैट्रिक्स नोटेशन ताकि वो भी थोड़ा थोड़ा हमें याद रहे। दिस इज ई आई जे, so it's a dyad, it's a second order tensor. So this means here I'm going to have E11, here I'm going to have E12, here I'm going to have E13, फिर E21, E22, E23, E31, E32, E33. Don't forget that that's how the IJ are going to expand out for each of the components here. So ये 9 terms हो गए उसकी। और हर एक जो है उसको फाइंड करने के लिए अब मुझे अगर मुझे E11 निकालना है, then I need to substitute I is equals to 1 and J is equals to 1 in here. Let's do that. When I do that, E11, so I get, oof, oh, ये तो, oh sorry, my point के I would have to substitute in here, but then also noting कि ये 1 और ये तो आ जाता, K here is a dummy, it's being repeated. मतलब ये कि K would go from 1 to 3 with a summation over it. So this does not make my life much easier, except कि we can do it. तो अगर हम चाहें तो हम ये कर सकते हैं, हम एक एक को लंबा चौड़ा लिख लिख के हम फाइंड कर सकते हैं। बट जस्ट अब अगेन आप लोगों ने इंडेक्स नोटेशन की थोड़ी सी प्रैक्टिस कर ली है। I want to jump to what those physical things are, right? So that's why I'm just going to write down कि उसका result क्या मिलेगा हमें. So when we do it, for E11, we would get this, which is del U1 with respect to capital X1 plus half of del U1 with respect to capital X1 squared plus del U2 with respect to capital X1 squared plus del U3 with respect to capital X1 whole squared. Right, okay, so something still pretty complicated. This is what is contained in this E11. इसी तरह I could also find E22, this one. उसके साथ भी I'm just gonna, apologies for this, I'm just gonna write down the result because the expansion will take me about 5 minutes to do. So for that I get this one. इधर सिर्फ U2 with respect to X2 आ गया, बाकी something looks very similar to E11. और E33 का इसी तरह हम expand कर सकते हैं. Right, okay, so we get the idea. This is just using the tools that we've learned for index notation to expand out what each of the terms are. So let me just get the result, all the results in. तो ये तो E1 ये diagonal terms का हो गया था. The off diagonal terms, noting के sorry मुझे इधर लिखने की जरूरत नहीं थी. I forgot to again note के it was symmetric था ना, ये मैंने अभी हमने थोड़ी देर पहले बात की थी वो break से पहले. So I don't really need these terms because they will just be, this one will be equal to E12, this one will be equal to E13, and this one will be equal to E23. So just having them in here, they expand out to be these. Now I hope कि आप लोगों को थोड़ा थोड़ा सा फायदा इंडेक्स नोटेशन का नजर आना शुरू हो गया है. पहला तो ये फायदा है कि जब कोई चीज सिर्फ टेंसर नोटेशन या डायरेक्ट नोटेशन में डायरेक्टली लिखी हो, इससे मुझे कुछ पता नहीं चल रहा कि उसके अंदर उसकी एक एक टर्म के अंदर क्या है. The only way to find each of the terms would be कि अगर मैं full fledged वो multiplication करूं, ठीक है. कभी कभी हम उस full fledged multiplication में interested नहीं होते, कभी कभी हम सिर्फ या तो उसको manipulate करने में interested हैं. ये manipulation अब आप, how would we have done this in direct notation? There just isn't any way. So we really did need the index notation to be able to manipulate it like so. Secondly, I may not always be interested in all of the terms. क्या पता मुझे directly किसी वजह से सिर्फ E33 चाहिए था. तो अगर मैं पूरी लंबी चौड़ी मल्टीप्लिकेशन कर करके फिर मैं मैट्रिक्स की इस टर्म को निकालने तक पहुंची, मुझे इट वुड हैव टेकन मी इवन लॉन्गर देन एक्सपैंडिंग आउट द इंडेक्स नोटेशन वर्जन ऑफ इट. ठीक है जी. So even though you might not be very familiar with it yet or comfortable in it, there is a reason as you will progress in your research career, और आप खुद जब कुछ let's say physical laws को manipulate कर रहे होंगे, you will start to see the usefulness of index notation. Okay. Right. So this is pretty complicated with, I don't know how, so we'll discuss how useful this may be. So let's get a little
मैम
move. जी please.
मैम यहाँ पे U क्या है?
Displacement.
ओके मैम, ओके.
So the displacements you remember ui was equal to small xi minus capital Xi, ताकि हम अपनी रेफरेंस से जो करंट में जा रहे थे, ये जो था u, ये हमें पता चल जाए. Right, because this was my capital X and this was my small x. Okay, right. अब वही मैं आपको I was coming to के this looks like a pretty complicated and unnecessarily long expressions. Let's just stick to the fact कि okay ये इसकी index notation में version है, और अगर हमें कभी कुछ इसका use करना होगा, so we can just use the index notation version for it. Let me just tell you though कि physically इन चीजों का मतलब क्या है. ठीक है जी. So उसके लिए ना you do need to take a look at these differentials a little bit more carefully. So what's happening in E11? E11 ये diagonal term है. इसको अगर हम देखें ना, तो इसके अंदर actually displacement in the one direction with respect to the one direction है. ठीक है जी, the position in the one direction. This is interesting because जब आप जैसे ही off diagonal terms पे जाए ना, जैसे E12, E13, E23, उसके ऊपर you'll see कि it's all the other terms. मतलब ये कि U1 with respect to X2 and X3 होगा, X1 वाला जो है वो as a linear term feature नहीं कर रहा. It's only featuring as a multiplication with another U1 with respect to X2. So this is a little bit useful to me because I need to remember that when I'm talking about these differentials, then उनके जो ये second जो squared जहाँ पे हो रहे होंगे या फिर ये दो multiply हो रहे होंगे, वो actually काफी छोटी terms होंगी, right? क्योंकि ये differentials हैं जो multiply हो रहे हैं. So let me just focus for a moment here on just the first linear term. So इसके अंदर this is the displacement in the one direction with respect to the x1 direction. Now again, sorry for relying on your prior knowledge a little bit, but जब हम अगर extension देख रहे हो in the one direction with respect to the one direction, मतलब ये कि extension u इसी वाली direction में with respect to this one, then I hope you may, अच्छा चलें, या फिर ये मेरा x1 था और ये इसकी displacement हुई है, then I hope you can identify that this is something which we more commonly are familiar with, just being some sort of a sort of tensile या फिर उसी axis के along, that is normal strain either as tension or as compression. Whereas if I look at, so sorry, I think I'm not being too clear right now, but just give me a few moments and I hope this will make sense. So x1 ka with respect to u1 is, it's as if this is the normal strain in the one direction. Whereas agar if I look at u2 और उसकी डिपेंडेंस कहाँ है, इस वाली किसी टर्म में आ जाओ, कहाँ कोई मुझे कहाँ मिलेगा, इधर नहीं मिल रहा. u2 with respect to x1, ये आ गया. इस वाले को देखो, u2 with respect to x1, मतलब u2 with respect to x1, अगर आप लोगों को याद हो तो this is my shear strain की type की term है ये. So basically what I'm trying to say to you, which is I think not being very clear, is कि just as you're familiar with the जो आप हम I think standard strain से familiar हैं, उसी तरह उसी तरह for E इसकी जो ये diagonal terms हैं E11, E22 and E33 for the green strain tensor, these three terms actually correspond to the normal strains. मतलब ये है कि if I look at my one face, oh कहाँ है one face? Oh sorry, ये x2 face है, sorry. This is my x2 face. If I look at my x2 face, then this E22 strain is telling me how much extension, yeah, compression, that is, how much normal strain is happening or occurring for this two face. Whereas, so diagonal components, these three represent normal strains, and these off diagonal terms, E12, E13 and E23, याद रखेंगे ये तीनों भी इन्हीं के equal होंगे. They are representing कि for example अगर मैं E12 को देख रही हूँ, then that's representing how my ये वाला this x2 face E1 direction में कैसे strain कर रहा है या deform कर रहा है, right? So that is showing me these three are showing me my diagonal strains, and these three are showing me my shear strains. So please always do remember this. Even for the green strain tensor, this is the case, right? Okay. Now let's come to the fact that so either you can just take my word for it, या फिर अगर कोई बहुत ही बड़ा green और Cauchy जैसे हम geniuses होते हैं और हम लोग पहली दफा ये चीजें derive कर रहे होते बड़े officially, फिर how we would have come up with this was by looking at कि ये terms क्या हैं. So U1 का change with respect to x1. That's why I was saying okay, U1 direction में x1. That's why you can sort of think of it कि physically इसका मतलब normal strain होगा. Whereas in वालियों में it's all the changes in the U2's U1 with respect to the other direction, let's say. Okay, but there's one more thing that we can find out just by looking at these expressions, which I think I've already pointed out, which is that these actually consist of, each of them, they consist of a linear term and then quadratic terms. Even for the shear strains, I can see I have two linear terms and then the rest are quadratic terms. So you may recall that if I have very small deformations happening, that is if these differential squared values or these differentials themselves are very small, that is there's actually very little displacement, u1 with respect to x1 is actually pretty small, then I can actually ignore these second order terms, right? So if I ignore those second order terms, then clearly ye second order term hai meri jisme product hai of the differentials. So I can just completely scrap this and just have my linear terms in there for the case when I have small displacement gradients. Matlab ye कि when these terms u, I, comma, j and so on are just, they're small, they're the case when I have small deformations. Then I can ignore those quadratic terms such that mera strain tensor is just composed of these linear terms. Now comes the interesting part, which is that please notice when I'm saying कि small displacement है ना, then उसको हम other words में ये भी कहते हैं कि it's just some sort of infinitesimal deformation. मतलब ये कि बहुत ही छोटी deformations हो रही हैं. why I'll come to just a discussion of why we might be interested in those. इस केस में this strain tensor is then no longer represented by a capital E because हमने उसकी एक approximation कर ली है. Instead, it's represented by epsilon, where epsilon is known as the small strain or infinitesimal strain tensor. और
मैम
ये
ये फार्मूले ये सारी फार्मूले की अप्रोक्सीमेशन करेगा, मतलब कि हमने डिस्प्लेसमेंट पे भी अप्रोक्सीमेशन यही होगी.
एक सेकेंड प्लीज नोटिस कि वो अप्रोक्सीमेशन हो रही है कि हमारे हमारी ये टर्म्स थोड़ी छोटी हैं, मतलब ये कि ग्रेडियंट ऑफ डिस्प्लेसमेंट विद रिस्पेक्ट टू डेल एक्स जो है ना, दैट इज del u with respect to del x is small. Okay, this is small. Not एक सेकेंड कहाँ लिखूं, u small नहीं कह रहे हम, not necessarily. Del u with respect to del x small है. फिर I can say कि जब मैं 2 दफा ये डिफरेंशियल को मल्टीप्लाई कर रही होंगी, then I can I'll get such a small value and I can ignore it. Okay.
Okay.
So it's the displacement का spatial gradient which is small. Okay, not u. So this is a very good point. Okay, some people sometimes tend to forget and say just small displacements, whereas it's not actually small displacements, it's small displacement gradients, which is of importance to us. Okay. So जब small displacement gradients हो तो फिर मैंने वो quadratic terms को ignore किया है. Right. Okay. I hope that clarifies. Okay. So then basically, as I was saying, in that case, when we have small displacement gradients, then we tend to represent our strain tensor with the epsilon symbol like so. और ये हमारा strain tensor है वो वाला जिससे आई एम श्योर आप सब लोग बहुत अच्छी तरह फेमिलियर हैं, एंड यू हैव एनकाउंटर्ड दिस फॉर a long time. And now let's see that small or infinitesimal strain tensor उसकी फिर terms क्या रह गई उसके अंदर. Of course ये मेरी वही expression चलती आ रही है just with the linear terms now. So I'll just show you shortly कि इसके अंदर क्या इसकी small strain tensor की एक term में क्या है. But I just want to point out right here कि why did we begin to discuss with E for this course? Because as you've seen, we've been setting up this stage by starting with complete sort of fundamentals. ठीक है, हमने कोई आमतौर पे हम already jump directly कि अच्छा जी ये strain होगा बस. Whereas that's not what we're doing right now. We've started to see कि ये सारे मतलब strain आया ही कहाँ से, and where have we started to try to define it, from the deformation gradient to the right stretch tensor to seeing what was the problem with that one, and then moving on to see okay, so there's actually a better, more easily defined measure of deformations, which is this green strain tensor. And what the beauty of the green strain tensor is कि उसके अंदर there was no assumption कि small displacement gradient है या नहीं. मतलब ये कि ये green strain tensor, that's the actual true strain which can be defined for any small or large deformation gradients. So this green strain tensor, that is the one that can generally be used for any problem, be it something जिसके अंदर बहुत ही ज़्यादा छोटे deformations हो रही हो या छोटे displacement gradients हो. Apologies for this, मुझे 2 सेकंड के लिए ना small displacement gradient को सिर्फ small deformation कहने दें, ठीक है? So for the case when we have very small deformations, or even for the case when we have large deformations, this green strain tensor is applicable for both of those cases. So if, as I said, you are going into a particular field such as maybe I'm trying to think, somebody is going into using some new materials which have very large deformations but have extremely high strength. So for example, वो fibers और इस तरह की चीजें कोई बना रहे हैं, right? Then of course उस case में you're going to get large deformations. So for that case, it's the green strain tensor which we have to use, because for that the small strain tensor is a very bad approximation. So you do need to be familiar that this is the actual thing which we're interested in, but often we tend to have problems in which the deformation gradients are so small that we can then just use this small strain tensor. Now this comes back to the case, okay, the vast majority of the problems that we deal with as engineers tend to be the problems for involving metals and ceramics, and I'm sure you're all you can all intuitively just tell, okay, because metals and ceramics have such high stiffnesses, unke upar when you apply even some meaningfully large loads, they deform very little. और इसीलिए for those cases we are very perfectly happy to just use this small strain tensor and make our lives easier. Okay. But if we, let's say, plastic molding के अंदर हम जा रहे हैं, या even for metals जब हम उनकी actual casting कर रहे हैं, ये कर रहे हैं, वो कर रहे हैं, for those cases then we do need to come back to our green strain tensor, because that's where we are going to have large deformations. Okay, right. So let's see कि small strain tensor के अंदर होता क्या है. अच्छा, another small note here. Okay, one small note here कि I've been doing all of this with my spatial gradients calculated with respect to the material definition, right? With respect to the Lagrange definition. The reason being, वही discussion जो हमने पहले किया था कि actually solids में हम अपनी reference configuration को ही use करते हैं, और ये जो deformations हैं, ये del with respect to del x, ये जो gradients हैं, sorry, उन चीज़ों में हम, sorry, ये जो spatial gradients हैं, वो हम solids के लिए ही interested हैं, ठीक? So इस वजह से we tend to stick to this. लेकिन nothing is stopping us actually. We could, if we wanted, to use the spatial gradient जो के spatial coordinates में था. Sorry for the two use of spatial. या Eulerian coordinates में था. इससे भी हम यही पूरा analysis करते हुए एक strain tensor को define कर सकते हैं. But it's just not very commonly used, because strains जो हम define करते हैं ना, वो हम solids के लिए define कर रहे हैं ज़्यादातर, और इसी वजह से हम material coordinate के अंदर ही gradients निकाल रहे होते हैं. So for fluids we're not so interested in these sort of deformation gradients and so on. Right, okay, finally, let's get to seeing what's inside the infinitesimal strain tensor. So this time around, मुझे actually, क्योंकि मेरे पास just linear terms हैं, it's much easier for me to plot those as well. So let me just show you. Okay, if I have a square block to begin with, and I consider its deformation, then what do और अभी मैं सिर्फ 2 directions में देख रही हूँ, not in 3D. Excuse my, so I'm just using it XY में, not in XYZ. So then clearly this is my it's my displacement in the X direction. So del UX occurring for an infinitesimal volume, del X. Whereas this is my displacement in the Y direction. And then finally, I just want to show you कि when I have those other gradients, मतलब ये कि Y displacement का gradient in terms of X component, then that's actually this angle right here that this side would make if it was sheared from its original position, such that now if I write down what my epsilon 11 is, epsilon 11, then please notice कि epsilon 11 का क्या मतलब है? It would be del u1 with respect to del x1 plus del u1 again with respect to del x1. So वो 2 times del u1 with respect to del x1 हो जाता. Hence that 2 multiplied by half would cancel out. So I would just get del u1 with respect to del x1. मतलब ये कि one direction की displacement del ux divided by del x. और यही this is I think I'm pretty sure you चले नहीं इतना इतने भी ऐसे assumption नहीं रहने चाहिए लेकिन I hope कि you all this looks a little familiar to you कि this xx strain is this, it's the change in the x origin, it's the change in the x length divided by the original length. Perfect. उसी तरह अगर मैं I'm not gonna find u22 and u33 because वो भी इसी यही expression with those coordinates आ जाएंगे and I think that's understandable for you guys. So let's move to the shear strain which is u epsilon 1 2 और epsilon 1 2 में अगर मैं substitute करूँ I is equals to 1 and j is equals to 2 then I get del u1 with respect to del x2 u1 comma 2 plus del u2 with respect to del x1 that is u2 comma 1 और अगर आप लोगों को थोड़ा थोड़ा याद हो कि एक जब हमारे पास इस किस्म की ये चीज़ आती है shear वाली displacement then जो shear strain हमारे पास होता है that's actually this change in the angle, it's the sum of this small change in the angle that occurs from the जो originally 90 degrees था और अब वो जो भी उसके अंदर decrease हुआ है ना that is our shear strain. So the only thing that's ended up happening is कि जो epsilon 1 2 है इसके अंदर actually उस sum का half है. This is just the new thing for us. Now बाकी सब वो वही it is still the shear strain but it's just half of the value that we are more used to. Now please note कि वो जो आम तौर पे हम लोग लिखते होते हैं उसको हम उस shear strain को हम gamma से represent करते होते हैं and this gamma is known as the engineering shear strain. Whereas ये जो epsilon 1 2 होता है this is the tensorial या tensorial shear strain और the only मतलब दोनों के दोनों shear strains है सिर्फ उनका बड़ी एक straightforward सी relationship है which is that gamma xy या gamma 1 2 जो है that's just equal to 2 times epsilon xy. Okay. So in common engineering notation, we tend to use the gamma, the engineering shear strain, rather than the tensorial shear strain. Now, as you can see, कि असल जो shear strain था, वो ये tensorial वाला है, because that's the one that's sort of coming from the step-by-step analysis of deformations, such that even कि हमारे पास shear strain की expression भी एक ही हो, strain की expression भी एक ही हो for normal and for shear strains. Okay, so I'm going to stick to using the tensorial shear strain for this course because I don't want to keep writing down a different expression for gamma xy, let's say. Okay. Okay, what's happening in rectangular? Oh yes, in यही अगर मैं x y की जगह 1 2 में लिखूं तो ये मेरे पास सारी की सारी terms expanded out would be these. Now again, as for the green strain tensor, these diagonal terms, oops, where is my, oh okay, I missed थोड़ा सा मुझसे इधर मिस हो गया. These diagonal terms are of course my normal infinitesimal, normal small strains. I'm just about to end. Please just bear with me for a few more minutes. And these are my shear, these off diagonal terms are my small shear strains. Any questions? Please keep an eye on your mics. Please do keep yourself muted. Somebody is unmuted right now. इसलिए मैं कह रही हूँ. Okay. So this वही के ये normal और shear strains कौन से होते हैं? This follows with oops. This follows. Oh. I disappeared for a little while. Am I back?
Yes, ma'am.
Okay, thank you. Right, so just to finish off basically, which is you're seeing this term pop up, which is the gradient of the displacement with respect to del x. इसको भी ना एक this thing has a name as well. Just as f was the deformation gradient, उसी तरह this or f के अंदर was del x with respect to del capital X. उसी तरह this gradient of del u with respect to del x also has a name. जिस तरह this was the deformation gradient, उसी तरह this thing is known as the displacement gradient. Okay, और यही चीज को हम अभी इधर पीछे यूज करते आ रहे थे. Right, so this displacement gradient को अगर मैं write it down like so, del naught u, where this del naught is as before just representing the fact that the del operator with respect to the capital X, the reference configuration. Okay, not the current configuration, but that's what the del naught is representing. Okay, what else have I got further than that? Ah, yes. Okay, now coming to this. So, so this thing is the displacement gradient, and now there's just one more last thing to point out about the displacement gradient. I hope you guys recall जब हम वो mathematical foundations set up कर रहे थे कि we can actually break down any rectangular matrix, or of course, एक second order tensor is a rectangular matrix, right? 3 by 3 होता है. I can always break down a rectangular matrix into a symmetric part and into a skew symmetric part, या फिर into an anti-symmetric part. और उसका वो breakdown या decomposition करते किस तरह है? उसकी expression के लिए you go back to the mathematical foundation one. It basically you guys take a look at that, okay? कि एक matrix का symmetric और skew symmetric part के अंदर क्या होता है? I'm going to try to write it down here, but I think I will forget. So if I say कि A symmetric plus A skew है, then it used to be that A is equals to half of, अब मुझे कोई याद कराएगा जरा, A plus A transpose plus half of A minus A transpose. I believe it was something like this, but I think कि मैंने ये वाला का minus yeah. Okay, thank you so much. So it was this basically, right? So now imagine कि मेरा A जो है ना वो ये del U है. कि मैं इस del U का symmetric और skew part अगर so please try to work through the arithmetic yourself. But what you will see basically is that this symmetric part turns out to be the infinitesimal strain tensor जो हम already देख चुके हैं, the small strain tensor जिसकी ये terms थी, right? And the skew symmetric part जो है वो भी, that's also something which is a little interesting. That turns out to be this जिस इधर हो गया ना ui comma j plus uji, मतलब a plus a transpose. Either I have a minus a transpose, right? So that's why I've got ui comma j minus uj comma I. And now this thing, just for your interest, is actually the infinitesimal root. It's known as the infinitesimal rotation tensor. Okay. Why did I bring this up? Just for your interest, के even this displacement gradient को जब हम break down करें तब भी हमारे पास interestingly हमारा infinitesimal strain tensor आ रहा है, just out of interest. और जो skew part है वो एक थोड़ी funny सी चीज है जो maybe बहुत ही कोई highly specialized लोग कभी use करें. जस्ट आप लोगों की रेफरेंस के लिए कि मैं एक ऐसी फील्ड में हूँ जिसके अंदर ये एक फिजिकल प्रॉपर्टी है जो एक्चुअली यूज होती है. So whereas it's not something which commonly pops up. Right, so I just wanted to point that out. What's interesting and what's happening is that we are defining loads of these physical properties, and now at least we're setting up the foundations for whenever we may encounter them or we may need to use them. The only issue is not everything is used in every single field, of course. There are some things, of course, जो हम सब बहुत familiar हैं. For example, the small strain tensor. लेकिन बाकी आप लोगों की specialized सब डोमेन और सब एरिया के ऊपर डिपेंड करता है कि क्या चीज़ कहाँ से यूज हो रही है. लेकिन interestingly, when we start off from just the first principles, at least engineering continuum के first principles से, then we can start to analyze the deformation or the kinematics of a continuum in this systematic stepwise manner and start to see कि okay ये इधर हम पहुंचे तो ये एक नई physical property आ गई है, इधर हम पहुंचे तो हमारे पास ये एक और नई physical property आ गई है, और उन सब चीज़ों के इधर उधर कहीं ना कहीं uses होते हैं. For example, I think सबको पता है कि strain tensor का कहाँ use है और कितना frequently use है. I hope you all remember our favorite Hooke's law, where we know that our small strain tensor actually causes stresses within a solid body at least. So उसी तरह ये जो बाकी चीजें हैं ना वो भी कुछ ना कुछ इधर उधर कुछ डिफरेंट मटेरियल्स में कर रहे होते हैं. जैसे मैंने आपको कहा कि मुझे W ये ओमेगा एक्चुअली ये यूज करना पड़ रहा होता है. Green strain tensor also for people who do large deformations, they will encounter it everywhere. Even U pops up for some people here there. So slowly we're setting up the entirety of continuum or entirety of mechanical engineering basically. Right, okay, so this is the end for today. Actually I thought कि I'd have time, तो मैं अपनी 7 बजे की break यहाँ ले रही थी, लेकिन and then I had a second sort of slides जो मैंने start off करनी थी, which were going to pick up from the infinitesimal strain tensor. But I'll end here for today, or I think you might have all, actually I don't know if you've heard, but anyway, so we'll pick up here next time. Again, just last thing that I want to highlight, okay, please also look at Reddy's book, which is this one. Okay, so Reddy ka kinematic wala is chapter 3, and I'm going to pop up in the slides that I upload today that it was 3.1, 3.2, 3.3 and so on, jo bhi sections hain, right? So you can see it's similar to lie, but just agar ek cheez ek se samajhna hai, our familiar deformation gradient right here, agar ek cheez